Statistics up there. So we are looking now at the presentation on model development. Sorted out, Prof? You are sorted out. So can we call your poster? Okay. Logistics up there. We are looking for the presentation of Prof. Peter Pensegrau. And the presentation or the poster is entitled New Methods to Assist Predicting Flash Flood Level. This one? This one?
They just had it now on the screen, but on the right-hand side. So I don't know.
Logistics, it seems that you had the presentation.
Sweetie.
So, logistic up there, we are waiting for two posters. One is model development by Mr. Teboho, and the other one is new method to assist predicting flash level. Yes, maybe let's try that one. No. we on, Prof? Okay. All right, so finally on new method for assisting to predict flash flood level. Prof. Peter, thanks. Over to you.
Good afternoon, everybody. I'm Professor Pansegrou from the University of Nelson Mandela University. I was head there of civil engineering. Now, this is quite an important topic these days. New methods to assist predicting flash flood levels. And the emphasis here is on predicting. Because it's no use after a big flood to sit in the comfort of your rocking chair and doing calculations and saying, yes, this was the 1 in 850 years flood, when thousands of people have drowned and many of them washed out to sea, never to be seen again. Some buried in mud, like we saw just 2 weeks ago now in Libya. So this presentation is basically a climate change presentation, because due to climate change we get bigger and bigger floods these days and more frequently. So our flood lines, they change. First of all, I'm going to pay more attention then to the importance of flash flood levels, thousands of lives that can be saved. Our president there with flood victims at Durban last year, and then direct and indirect flood damages. But I also discovered a new big cost there, which I've never seen, so it might be interesting to you, and perhaps people who are interested in more economics, but engineering with linked to economics may find it interesting for a master's or a doctorate or so. And then the benefit cost ratios of this prediction are very high, 10 to 560 worldwide. Why? Because it's very cheap, actually, to predict the costs. But the benefits of that are millions and billions and sometimes, well, I wouldn't say trillions, but trillions for the whole world, yes. Now, in view of that, I've developed 3 methods. That's what I'm going to present then in detail. The first one is maximum precipitation rate method, MPR rate. I was an RE in Johannesburg, and we had a big flash flood there at our site. I personally took the measurement that morning between 8 o'clock and 8:20, 40 millimeters in 20 minutes time. So it was 2 millimeters per minute. And I thought it was a terrible flood, but I couldn't see the offices from here to that door, say 30 meters away, 20, 30. I couldn't see the site labs a bit further away. So I got interested in this, and I said to myself, I'm going to find out the maximum, the MPRs over the whole world. And I was surprised that for the African context, the MPR there at Reunion in 1966 was already 33 millimeters, 33 per minute, and then the world record at the moment is 38 millimeters per minute. So I ventured and I said, okay, I'll then define the speed of light for flash floods to give people a bit of comfort in a certain sense that they know what is the maximum they can expect, and that is then 5 meters in one session of rain. It depends. It's only the morning, the whole day, but it can go up to 5 meters. But not more at this stage, 2023. Could be quite a lot more in 10 years' time or 5 years' time. So you mustn't quote me, but at the moment, as far as I'm concerned, the speed of light for flash floods is then 40 millimeters per minute. If you have MPRs for your region, your drainage region, it's very easy to calculate then the flood rate. And the flood rate is usually our problem. Then I thought to myself, okay, we don't always have these, unfortunately. We must quantify our drainage regions much better. So what is the second thing that I can use? Return periods. You know, in South Africa, the return period is 1 in 100 years. I found that is too low. Definitely too low, because I did a study of all our big floods during the last 53 years. First flood I was involved in was in 1970 in the Eastern Cape. They flew us with helicopters in military helicopters to save people. We saved quite a lot of people, Shalumna, that area, up to Swelitsha, the old King Williamstown. So, but I found then with this research that return periods are also not, they are erratic and sporadic these days. You can't trust them anymore because of climate change. So I thought to myself, well, now I must go back to another empirical method, which I called the D4RR method. Doubling 4RR is river regimes method, where you take your river and you subdivide it into the upper regime, middle regime, lower regime, and exit regime, and then you have flood depths there. Very easy to remember. You just remember the first figure, 2.5 meters, and you double each time, 2.5 to 5, 5 to 10, 10 to 20, 20 to 40. And it wasn't long after I have sort of formulated this that the people at Moramela, the councillors and so there in Mpumalanga, next to the Bergslug potholes, phoned me and asked me whether I can quickly, in 1 day's time, give them the flood levels, flash flood level of that place, that town, because they expected a huge flash flood the next day with rivers coming down and weather services and so on, which I did then. And I applied this, got this, and it worked very well. I got a flash flood level of 1160. The water came up to 1158, in other words, 2 meters lower. And the people said to me, yo, Prof, how can you now say how high the water will rise here? I say it's through mathematics, it's through science, and through engineering, water engineering. So if your children can do it, you must advise them and give them support to do these calculations. Method 3 is the conventional flood level computer programs, but there I say there are 2 important changes that I have realized with my research. And these 2 important changes are so significant that I say it's a new method. I haven't developed these programs. There are many of them these days in the market. Each month I see a new name, but you must use them correctly. And the 2 important changes there is you must use the best flood rate cubic meters per second, like from this MPR, if you've got it. If you haven't got it, you must see you must go to records, you must get advice from weather services, from hydrologists or so. You must get the best flood rate. But then, this is very important, you use the absolute roughness K values of the rivers, and you measure them at each cross-section, and then calculate your Mannings in friction coefficient. You can go on to the next slide, if you can manage that. Most engineers use Mannings equation. You know that you can use Chessy's flow equation, you can use Colebrook-White, you can use Darcy-Weisbach. So there are also a number of these flow equations that you can use, but the big thing is you must measure the K values, because that is where the present, I would say, theory, I can say, the formula, where they fall short. You see, while they are taking their time there a bit, the thing is, after these big floods, usually you get these engineers, politicians, and so on saying, oh, this was such a terrible flood, and we never expected it. We never thought it would happen to us. But I don't like that anymore. It must be done proactively, as I said there, proactively. No, they moved it up. Proactively, before the time. And you must, when there's a flood, you as engineer or as politician must get up confidently in front of the TV cameras, and you must say, yes, look, we predicted the flood level to be there. And we did have now an enormous flood, a flash flood, but the level is here. That is where the water came up, like I also did with the Moramella case, where the water came up to 1158 instead of 1160. Thank you, yes. Okay, this can quickly, I'll take a bit too much time, but this is the still part of the third method, where I said we must calculate the N value. I developed this friction coefficient equation. I called it the rationalized friction coefficient equation for Mannings N. It's in the metric system, MKS, so the K value is in meters. And it's actually not a difficult formula or equation to remember. It's just N equals 1 over 22.5 log 4 over K. And the log is the base 10. And now engineers always ask me, but show us and teach us how to get that K value. Then I say, okay, you take your cross-sections, you measure the K values, the roughness, absolute roughness, and you take the measurements of their lengths, I would say, and this is a typical cross-section, and then you multiply the Ks with the Ls, K1 plus L times L1 plus K2, L2, and so on to K7, L7. In other words, you do a summation of that, and then you divide it. I don't know, there was a line here. It disappeared. You divide it by the whole length there. I called it L, the whole length. I know you people may say, but why didn't I call it P for wetted perimeter? The problem, which you are used to, the problem with that is we don't know exactly how high the water will come. It may come here, it may come there, it may even go a bit higher up. But I always say to engineers, go as high up as possible. I mean, not unrealistically, but go high up and do a decent job and get it, divide it by the L and get this K value, put it in there and you have your N value. So this is the only equation that I'm aware of that is valid in the extreme rough turbulent flow zone. All the others, and they are good ones, but they just go to the end of the rough regime. But then there is the extreme rough flow zone now, these days with floods, big floods over the world. The old theory, the theory may still be basically the same, but the friction coefficients suddenly don't work anymore because they were developed more for concrete and pipes and engineering material, if I can put it that way, and a little bit also for grass and natural roughness elements, but certainly not for huge reeds and trees and big roughness and even buildings. Here you get your buildings as well, eh? So, and they are sometimes inundated, the houses are under the water. So that is where the change comes in. This is a new development, and that's why I came to represent it here at this conference, because I feel it's an improvement on, existing knowledge. Thank you.
Thank you so much, Prof. The next poster is Mr. Teboho. Mr. Teboho. It's a poster on the model development, evaluation, and optimization of nutrient removal in a single and double stage strategy for sequential batch reactors. Okay, over to you.
Afternoon, everyone. My name is Teboho Jakuja, and then I'm honored to present my work, which is modeling, development, and evaluation and optimization of the nutrient removal in a single and double stage reactor. So I'll start with a quick background. The wastewater contains harmful substances which actually can impact your environment. Therefore, it's very important that we treat the water and then we dispose the water in the controlled manner. In South Africa, wastewater is governed by water use license, which is issued by Department of Water and Sanitation. So the water use license depends on the classification of a specific plant and also the catchment area. This one I just...
Okay, then speak into the mic.
Okay. So can you hear me now?
Yeah, but they are recording, so they need to be able to hear you.
Okay, sorry for that. So in South Africa, we use water use license to govern our wastewater effluent qualities, which is issued by Department of Water and Sanitation. So this is governed by general limits, where we actually we use the water, we discharge the water in our reservoirs, and then we are recycling that water back to our processes. Normally, we have to comply to the general limits. The general limits, for this study, we will be looking at ammonia, which should be not greater than 6 milligrams per liter, and then also for your nitrate, not more than 15 milligrams per liter on the general limit. However, we are struggling with the special limits where we have places where we have wetlands, those are very sensitive catchment areas where we actually have to meet the special limits according to Department of Water and Sanitation. And those special limits on our ammonia, we are looking at 2 milligram per liter, and then we are also looking at nitrate at 1.5 milligram per liter. So for the focus of the study, we are actually looking at sequential batch reactor. The sequential batch reactor has been applied by most researchers and industry because of small space that is required as compared to the conventional activated sludge, which most industry in the old time they used to use. So with the sequential batch reactor, because of less space, all the reactions, biochemical reactions, are actually taking place in one reactor. So with that said, this reactor, although it has its own benefit, there are issues which are related to it, that it cannot actually treat the high ammonia wastewater because at the end of the cycle you have high retaining nitrates, or you can also have both nitrates and ammonia. So I've looked and tried to find models which can help us to actually optimize the process, but I haven't found one specifically for sequential batch reactor. However, I found one for activated sludge, which was the study which was developed. So it's very complex to actually model the biological reaction. So to reduce that complexity, I use system dynamics approach, which deals with deals with the stocks and flows. So this is the SBR reactor, which was selected with one inflow, and then this is the outflow. And then how it operates, the reactor, you actually feed your wastewater into your reactor, and when you have reached the highest volume of your reactor, you stop the feed, and once you have stopped the feed, you start your aerators. That's when now you start your process of nitrification, where you convert your ammonia into nitrate. And when you convert your ammonia into nitrate, you are forming nitrites as in the same time. And then at the end of the cycle, you stop your aeration and then you settle. Then once you have settled, then you do your decanting and then you remove the clean water for disinfection. And then so this is the particulate matter stock. This is not another reactor. It's just showing you that this one has its own independent concentration, which changes in all the phases of the reactor. And then when you look at this one, is also the substrate into inside the SBR, which is the reactor. So all these reactions are taking place inside the reactor. It's not an independent reactors. And then you have your ammonia as well, which is also taking place inside the reactor, and your nitrate taking place. So you can see the complexity of these microbiological reactions, how they interlink with each other. However, I will explain this graph. I will explain this graph. As you can see, this is a typical, this is the results which was obtained from using activated sludge model to try to achieve, to simulate the SBR, how it should operate. So with that said, during this study, as you can see, this dotted line, it represents the ammonia loading into the reactor. So this is the ammonia loading as you are feeding into the reactor. And then at your highest point, this is where you stop your feeding into the reactor. And then your nitrate, which is represented by this line, then you will start to see a decrease. The reason why you see a decrease is because from the previous cycle, they had 8 milligram per liter, which was remaining inside the reactor. So when you actually feed your raw wastewater, you're actually consuming the oxygen that is in the nitrite, so that you are actually enhancing the denitrification process, where you are actually removing the nitrogen into the system. So during this process, when you stop your feeding here, you will start to run your aerators to start your nitrification process. Then you will lose your ammonia, as is indicated here, and then you will form your nitrite, as indicated here. Then you will start to settle at maybe 0.4. You will start to settle your reactor, but the concentration then does not change. So at the end of the cycle, we have problems when we have high ammonia in our raw wastewater, because then we always have low ammonia, but we have high nitrate that is retained. So the model which was developed, actually this is the results, but in this model it was assumed that there is no nitrate which is retained from the previous cycle, and then we were able to achieve the same behavior. This is when we are feeding up to the top, and then you can see the level of nitrate is still at 0, but once we start our aerators, we will now lose the ammonia, and then we will form the nitrate. So this is the problem, because our retaining nitrates will be high. Sometimes it will be above 35 milligram per liter, and then we need this to be at least lower than 2, lower than 1.5. As ammonia, we want it to be less than 2. So with that said, we wanted to add external carbon source, which can help us to reduce. That's when we started to introduce the second feed into the reactor. And this is just an indication to show you, this is the first feed into the reactor, which is represented by this figure here. However, when we do the second feed, as done previously, this is the first portion on the right-hand side there. You can see this is now the decrease of nitrates, as explained before. And then this is, okay. Sorry. Okay. It's going. So I will just explain. So on the figure that shows double peaks, then you see the first reaction is actually the same as this one, but on the second one, when we have high concentration of our nitrates, we actually feed raw wastewater into the reactor. So by feeding that raw wastewater into the reactor, we are actually reducing the concentration of the nitrates further to come down to minimum of 4. However, at some point, you will now start to aerate, because you have introduced ammonia also into the system. So when you start to aerate, you will lose that ammonia from there, and then you will also increase a little bit on your nitrate. So I simulated the same scenario using the model, and then the results are indicated in this figure here. As you can see, the same peaks that were achieved from the top were achieved here. However, in this case, we were not meeting the special limit as required by Department of Water and Sanitation. So during optimization, so you can now control here how much you are feeding in your second phase, in your second feed, so that you can keep your nitrate as minimum as possible. As you can see from this figure, that we have actually achieved to meet the limit, which is required by water use license. And also on the last figure, we can actually achieve even lower when we are feeding for a short period of time, and then we are also not even aerating at that period. So we are able to achieve a high concentration of nitrate. So this study can be used by policymakers who wants to develop policies in terms of the treatment of wastewater. And also the engineers can use this model also to optimize their existing plants to make sure that their plants comply to the water use license as a requirement from Department of Water and Sanitation. That is all from my side. Thank you.
Okay. Those are the posters that were available this afternoon. Unless someone else has got a poster here and has not been given the opportunity to present his work or work. Right. So for the poster session, the idea was that the researchers and the presenters will stay behind. We have these posters in the traditional format on the stand here. They will stay behind, and if any member of the audience has the intention to interact some more with the presenter, they are welcome to come in front and to discuss and probably find out a little bit more. That's the idea of this session. On that note, let me say thank you very much for everybody that attended this session, and thank you very much to all the colleagues that managed to present. It is very much appreciated, and I will invite the people to give them another round of applause to say that they've really honored this session. Thank you very much. The session has ended. If you want to interact some more, you are welcome. I have an announcement just to say that the main session that was scheduled to take place in this venue has been cancelled, so you have the afternoon off. Thank you very much. Bye-bye.